Alright, so we know that there are different methods of material selection a lot. We have materials indices, right? Materials indices, we have the decision matrices, artificial intelligence tools, computer design, a whole lot. These are just a few. But then, in this discussion here, the ones that we'll be using to demonstrate a way of doing it will be computer aided databases, and then we use it in conjunction with what we call the performance indices, right? Yeah. And then when we are actually doing this computer aided databases, right, using the performance indices or generally the computer aided database, there are general stages that we follow, right? Translation, screening, ranking, and documentation. But in this case, we won't be talking about the documentation, so we're talking about translation, screening, and ranking. So in every design case, right, there are design requirements, right? So whoever will design it, or the architect or the mechanical engineer, will design it to specific requirements, right? And then what happens during the translation stage is that we transfer these design requirements, right? We convert it, the right way to be to convert, right? So let's say that way. To change this design, will be to change this design requirements. Let's see. Right. A minute. Will be to change this design requirement, right? We change this design requirement to what we call constraint, right? So based on all that the design says about it, we change it to constraint, and these constraints are what restrict us to actually select or do whatever it is that we are doing the design selection, right? And then after we've applied this constraint, right, what happens is that we get a whole lot of materials, right? But then depending on all the constraints and whatever it is that the material will serve, we take some of the what do you call it, some of the materials away. So when we are taking some of the, so like kind of like we remove some of the candidate, or let's say reduce the candidate material. So let's write it this way: reduce candidate materials, candidate materials, right? So we basically reduce their number. So during this time is what we say that we are doing the screening, right? And when we do the screening and reduce the number drastically, we left with specific materials, right? So here, let's make it something else. So we reduce the suitable materials here, let's say that way, right? But then when we reduce it, there will be a specific number of materials that we get, a smaller one than after the screening, than before the screening, right? And these ones are what we call the candidate materials, right? So when we get the candidate materials, what we do is that we arrange them, because here we are using the performance indices, we arrange them based on the performance index that we are using, right? So we get candidate materials, right? So we rank them, right? So candidate materials, let's do it this way, are sorted. Yeah, let's use that word, sorted based on the performance index, based on let's write performance index, right? Yeah, based on the performance index. And then we are going to use an example to demonstrate all that we are talking about here, right? Yeah, so let's see. So in this case here, the problem is that we just need a component, right? This something like this that will be under tension, but then the main thing is that we want it to be what, stiff and then light, right? And then other things have been said as well. So you see, it's to be a bar, and you're saying that the bar, right, must not, during the service, must not extend beyond this, right? And then when it's working, like on the surface, the function that the force that it will be experiencing will be this F constant, and then this will be the length, the initial length of it, right? Yeah. So looking at all this, some of the constraints have been given. So the what we will be doing now will be the translation. So the translation is that we need a stiff material, right? So if we need a stiff material, let me arrange this, right? And then looking at the diagram there, it's just giving us more parameters, like, oh, the whole problem has been described in terms of the component, right? Yeah. So let's see. So it means that everything that has been described here, they want it to meet a particular requirement. So anything that is not described, right, mean that it's free. It's a free something that can change depending on design. So let's see. Looking at the diagram here, we see clearly that what's the name? Force has been specified under the working condition. The what do you call it? The extension has been specified, right? And then the L has been specified around as well. So the only thing that is free here will be this one, right? Which is kind of like the dimensions of it, right? Yeah. So let's see. So the whole problem is saying that we need the component to be stiff and then light. So based on this to select the materials, right? So let's see. We are going step by step. So stiff, a material property that we can think of, and as we said, whatever it is that we are doing here, we are doing a computer aided, we are using computer aided database, right, with the aid of performance index. So what it says is that the whole computer system or the software has what we call the database, and in this case we'll be using answers. Look at it. So using the database, and because we are using the materials database, what it will mean is that we will have a lot of these material properties, right? So we are using computer aided system with a material database, right? So let's see. So we want it to be stiff and light. So stiffness will be related to a material property that we call Young's modulus, right? Or modulus of elasticity, right? Which is this, right? And then when we are talking about lightness, the material property that we can talk about, let's see, can be, let's say, want it to be light. So that means I want the mass to be low, right? So we can talk about mass here, right? So that means that based on the design, we want the stiffness to be high, right? And we want the mass to be what? Low, right? And then the equation that can describe this modulus elasticity is stress over strain, right? And then the mass here is what density times what volume, right? This is the basic equation that describes it, right? So now let's go one by one. Looking at this side, so now we are on this side, right? So looking at this one, the Young's modulus, right? What we see here is that if we are using E, right, it will mean that there's a material property, it doesn't change, right? Yeah. And then whenever we are doing this thing, there are some of the parameters that we must take out because we cannot, because those ones can be changed, right? So definitely we maintain this because it's a material property. We have to keep it in what we are doing, right? And then the strain here too, there's something that this one is just strain, right? But there's something about the whole condition I was given that says that it shouldn't extend beyond something, right? So meaning that some of them are constraints, right? Or they must appear in whatever it is that we are doing. The only thing that is free here, it wasn't specifying the stress that the material will experience. So this one here, somehow we must take it off what we are doing, right? So this will happen. So if we are taking this off, we kind of make it a subject. So it happens to be this way. Stress will be what? Young's modulus times strain, right? And let's go to this side. And we know mass, right, is equal to density times volume. Density is a material property, right? We keep it here. We weren't given any volume, but we're given a lot of parameters to describe it, right? So looking at this, we said length is fixed, right? So let's put length. So volume is what? We know that volume, let's see, volume is length times area, right? So here we will have times length times area, right? But then we were given length, we weren't given area, right? So we're given this, and then when you are doing all these things, you must exhaust all the variables that were given. So we are trying to exhaust everything that was given to us, right? Length, and the area wasn't given, but we know the cross-sectional area will be by multiplying these two, right? C by C, right? And that will give us what C squared. C squared. Right. So clearly here we know that this must be eliminated. This stress here must be eliminated. So we make it a subject, right? And then here as well, we know that this C squared here is a free variable. Like they didn't specify it. So that one too must be eliminated, right? Yeah. So we make C the subject on that side as well. So we have C. So let's see. But for now, let's maintain we've circled it so we know what to eliminate. Right? So when we get here, we know that we must eliminate this, right? But then again, we know this stress to be the same as force, right? So then again, we are still trying to exhaust everything given to us, right? So force, right? So let's see the ones we've eliminated. So force has been eliminated, right? This C has been taken care of. We talk about it. Length as well has been taken care of because of this one, right? So let's see. The only thing left will be this strain here, right? So let's see. So force, and then we know this stress is the same as force per unit area, right? Yeah. So now it's the next thing for us will be to eliminate this one here, right? So let's see. And we know that's extension, right? And then we know this one to be E, and then this one is the string, so that will be change in length. So we know this to be change in length over initial length, right? Multiplying all this, right? And this all will end up being E, right? Times what we have as the extension that was given as this one here, right? We are using everything given in the what do you call it, the design, right? So that will be this all over length, right? Initial length, right? So we have that, and we know this stress again is the same as force per unit area. So meaning that everything given to us has been eliminated, sorry, has been included in what we are doing. And this one here as well is not defined, so we use something that's already defined here, right? So this will be F, and the cross section area, we know that to be this one right here, right? So we end up having what here, C squared, right? So the C squared has appeared in this side, right? Right. So now that we have this, we can make what's the name, we can bring whatever the C that we have here from all this side and put it in this mass here, right? That's what we're trying to do, right? Because we know that we are trying to eliminate this one right here, so we don't use this side of the equation to continue what we are doing, and then we can replace this with something from this side to eliminate this. So we are trying to eliminate everything that we can, right? So let's go over it one more time. Our aim is to eliminate this because it is not described in the system, and then this one is a free variable. We want to describe that, we want to take that one out as well, right? So now let's see. Fine. So now that we have all this, we know that this C can be gotten from this side, right? So we end up getting what, and this is stress, and we know that this stress to this side is equal to all this, right? So these two are equal, right? So we end up getting, let's see, let's cover this side. So that means that we have E, right, times extension on L being equal to F on C squared, right? And then if we make C squared the subject, we have let's see, we have E, right, and we have E, right? We're trying to make C squared the subject. Okay, right. So C squared the subject, that will be, we have F, let's write this one. Okay, so then we have C squared being equal to F, right, times L times what, so F times L, right, and then we'll have E, and then we'll have what, extension at the bottom, right? F, L, E, and extension at the bottom. Let me write this extension also is clear. Right, so now that we have this, and our aim, as we said, is to eliminate these ones. So now we've taken care of this. The next will be to take care of this in this equation here, right? So we translate all this here. Oh, sorry, we not translate. We actually replace all wherever we have the C plus in this equation up here, right? So that's what we are doing. So let's see. So when we put C in, we end up getting mass to be equal to density, right, times length, right, times all this, which is F L, right, and then we have the elastic modulus, and then we have the extension, right? So now everything here is something that was given. If they are not, then the rest will be material properties, right? So that's what we have here. So now that we have this equation, there are a lot of things that are good that goes into it. So now there's the equation that we have now. The equation that we are concentrating on now is this, right? But let's see. Okay. So whenever we are doing this material selection process, there are some things, there are a lot of properties involved, right? So some of them are material properties, so we call them function of material, function of material properties, right? And which of these ones are material properties that are constant, right? And those ones are the ones that we can sort of like group them out, right? So we know that let's see, the ones that are material properties are, what do you call it, we have density, right, and we have Young's modulus, which here and here. So how they appear in the equation, how we write them, but we bring them together. So we have density on E, right, and we have some of the parameters that are based on the function that the material will be serving, or the service conditions, right? So we call them function of function. And when we look at this equation that we've put in the rectangle here, the ones that are function of function will be just the force, because the only thing that will be appear in the service condition will be the force, right? So just force, right? And we have some other thing that we call function of geometry, right? So based on the dimensions of the whole part or the whole component, so this is the whole component, some of them are just dimensions, so that will be the L, and then the extension, right? Those are the ones appearing in the equation, right? So here we have the function of geometry. We have what's it? What's it? We have the length. So here's L squared, right? So all this change to L squared. Let's write it this way. So yeah, L squared. So here function of geometry will be L squared, right? And then let's just put it here, will be the extension, right? Yeah. And I remember when we were doing all this, we said the process that we are using now, or the material selection method that we are using now, is what uh computer aided database, right? Using performance index, right? So if you have a database then of materials, they mean that the one that we'll be using is what we call the function of materials, which is this, right? And from this we formulate what we call the performance index, right? So now let's talk about that one, right? So meaning that we are using this the function of material, right? Function of material properties, function of material properties, and in this case we call it performance index. Let's give it a p, right? But in some cases it is called a metric, right? A metric. This is what we are using to, as we said, there are various stages in the material selection procedure. So now we've done that will mean that we've done the translation, right? But we need some kind sort of equations or some of sort of things to do the screening and ranking, right? So yeah, let's see. And at every point we talk about what we are doing. So now that we have this performance index, we are going to use it to do the ranking. At the same time we use a form of it to do the screening as well, right? And then we'll go to the computer system to see that we actually open the software to see, right? So here is what we call the performance index, and in some cases we call it the metrics, right? Yeah, the metric, right? Or the performance metric or something, right? Yeah. So yeah, let's see, which is this equation that we are seeing here to be the density over what, the elastic modulus. Fine. But remember, when we started the whole thing, we said the aim was to do what, to make sure that we have a material that has a what, a high stiffness, and then density that's low, right? So we said a high stiffness, we want high stiffness because to be is tension, right? And then what, the density to be what, low. But then when you look at this equation here, or this metric that we have here, right, what it will mean is that what the software does is that whenever it has this performance metric, it has it in terms of a value. So let's say if you have materials, let's say A, B, and C, right? So these are the materials, right? And then each of them has density, right? Each of them has a Young's modulus, right? And then we are doing what we call P on E, right? Because these are constant, these two are constant, we have a value for this one here, right? And then based on this value, it use the one that has the highest value of this to rank them. So if it happens that this one has, let's say material A, right? Material A, B, and C. Let's say this one, material A, has this density on elastic modulus to be, let's see, to be, let's say 2. This one has it, B has it to be, let's say 1, right? And then C has it, let's to be 4. When it is ranking the materials, it will be this way: C, and then we'll go to A, right? And then we'll go to B, right? So mean that to rank it in this way, and the one that will appear at the top of the ranking will be C, right? Will be C, right? But if it happens to be C appearing at the top, that will mean that C has a low density, right? Because if the density is low, meaning that if this value here is high, if this P on the density in, if this density on the last stiffness here is high, it will mean that this Young's modulus here is low and the density is what, high. That's why this one here is high. But that's not what we are looking for. We are looking for, so let me write this here. If this value 4 here is high, it will mean that this density here is what, high, and then the stiffness is what, low. But that's not what we are looking for. Our aim is to make sure, this is it, that the stiffness is high and the density is low, right? So that's where we do something we call, we invert this whole thing. So instead of using this density on E, we change it, and then we use E on density, right? So that's where in this case sometimes somewhere you see that the terms as this one will be to minimize, and then when we get to the graph in the software we see why we say it that way. This will be to minimize, right? And then this one right here, the one on the right, will be to maximize. We'll see what happens when we use the software, right? But this is the whole foundation behind, this is the whole understanding behind it, right? So that's why we won't be using this, right? But we won't be using this, but we will use this when we are talking about the software, right? So we know that this one here, this E on P here is what we are using, the performance matrix that we are using, right? So and the performance matrix we've given the symbol M, right? Yeah. But then that would mean that we use the value for just this to rank, right? But when it comes to the screening, there's a portion of this what was it? There's a way to transform this equation here to suit the form that we can use it for screening, right? But so let's see. Right. So then what we have to do is that we have to turn this whole equation to something that looks like y is equal to mx plus c, and then we are familiar with this equation to be the equation of a straight line, right? And we know that the only things that we are interested in is we kind of like change this, and then we see the value that we get for y, right? So in this case, the two things that we are interested in is this stiffness and right, this stiffness here, and then the density. So one way will be to that we make one y, we make one x, so it can be anyone for you, but it is what we use in the software to do this, to do the screening, right? So in this case, let's see, let's choose to make our e, right? Let's choose to make our e the y, right? And we'll make the density the x, right? The density. So that will mean that whenever we go to a software and doing the graph, we'll put the e, right, or the stiffness on the y-axis, right? Because we've given it to this one, right? And we'll put the, what's the name? We put the density, right? The density on the x-axis, and then from there we'll do the screening, and then we'll do the ranking, right? So that's what it means when we're doing this, right? But we're not done. We have to transform the equation for us to get some sort of slope, right? So now let's see. Let's clean this up. We know that we need this too, right? Yeah, we want to transform the equation to this form, right? So we have that means we have to make e the subject, right? Because we are making e what our y, we are making density what our x, right? So let's make e the subject from this equation, right? So e will be equal to m times density, right? Fine. But then to make it much more simpler, because we know we are making let's continue. Right? So let's see. Fine, I want to change it to this form. So we can take logs. So when we take logs, we have log of e, right? And then log of all of this, log of m and p will give us log of m, right? Plus, there's no p, this is density, sorry. Right, yeah. So log of m plus log of what? Density, right? But our interest here is what the y and x, which is e and density, right? So when we rearrange this, we get log of e being equal to log of the density plus the log of m here, right? Yeah, so now we have it similar to, what's the name? Y is equal to mx plus c. So this here is a constant, right? And this here is mx. That will mean that our slope here will be what? Our slope, which is m, will be equal to 1, right? Because 1 is here. And the log of density is our x, right? So these are the two things that we'll use to screen and to rank, right? So let me write this well. So we've done the translation. So translation has been taken care of. So the stage is translation, right? And then we do screening, right? And then we do ranking. We are not doing documentation here, right? So we've done the translation already. What we use for the screening will be this slope m is equal to 1, which is the slope, right? Yeah. And then what we use for the ranking will be this equation, the Young's modulus on the density, right? So these are the two things that we'll be using. So now that we are done with this, we are going straight to the software to see how we use them.